I'd like to just recap the quantum hotel. Because we've been talking about shells and subshells and orbitals and electrons and their spins and everything. And it's a lot to keep straight. And so that's why I wanted to relate it to something where the organizational structure is similar, but we understand it because I think all of us have either been to a hotel or at least seen hotels in movies or something, right? So the floor in a hotel is like the principal shell in the quantum mechanical model of the atom. It's the main levels of energy. As you go higher on the principal shells, the energy of the electrons there increases. In my analogy, money is equated to energy. So the higher floors cost more money to stay in. Okay? Maybe they have a better view. Make up your own crazy reason. The rooms on each level, on each floor of the hotel, are the subshells. Those are the ones with the letters S, P, D, and F. So on each shell, there are subshells. On each floor, there are rooms in the hotel. In each room, there are beds, right? So the beds are the individual orbitals. The S subshell only has one orbital. The P subshell has 3 orbitals. The D subshell has 5 orbitals. Those are odd numbers, 1, 3, 5, and the next one's 7. So those rooms in the hotel correspond to the S, P, D, and F, and instead of having numbers like a regular hotel, they have letters. So the S room has 1 bed. On every floor, there's an S room that has 1 bed. P rooms have 3 beds, D rooms have 5 beds, F rooms have 7 beds. And the rule is you can only have 2 people sleeping in a bed. Nobody's allowed to sleep on the floor or anything crazy like that. Okay, so there's only 2 electrons that can be in one orbital. The electrons have to have opposite spins. The people sleep head to toe in the bed. Okay. So here's the first floor of the hotel. There's only 1 room. It's the S room. It's got 1 bed in it. The line is representing the orbital. The second floor of the hotel, here's the S room. It has 1 bed, 1 line, and the P room has 3 beds. There are 2 rooms on the second floor. The third floor has 3 rooms, the S room, the P room, and the D room. S has 1 bed, P room has 3, D room has 5. On the 4th floor, there are 4 rooms. We're only showing 3 of them here, but there's the S room, the P room, the D room, and then there's another one, the F room. The F room has 7 beds. The energy levels here get a little jumbled up because of the interactions between the electrons. It gets kind of complicated. So as you go up in this graph, it's increasing energy or increasing cost to stay in the room. So the S room is cheaper than the 3P room, the 3S than the 3P. And you might expect that the 3D would be the next most expensive, but it isn't. The 4S is next, and then the 3D is after that. It's some weird pricing scheme, okay? The hotel made up, yes.
And is that word or something to memorize, or is there a method?
There is a method. You don't have to memorize that. It's all on the periodic table. So let's talk about the order. One method is to draw a diagram like this. So there's a pattern here, 1S, then 2S, 2P, 3S, 3P, 3D, etc. And then to do the order, you start diagonally 1S and you come back up 2S, 2P, 3S, 3P, 4S. If that works for you, great. I'm going to show you what I think is better. It's all hiding here on the periodic table. Now this one's color-coded to help us see it more clearly, but you can get the same information off of just a black and white periodic table. So these 2 columns of the periodic table, and here we see that helium kind of belongs over here. These 2 little guys, they kind of jump around We're not sure where to put them because they fit in different categories in a way. So let's just mentally move helium over here. So he's blue, there's helium, and I'm going to cross him off over here. Okay? So here we have two columns. This is the group we call the S block elements. There's two columns. S orbitals hold 2 electrons. In the pink, we have 6 columns. These are the P block elements. The P room has 3 beds. It holds 6 people. The P subshell has 3 orbitals. It holds 6 electrons. There are 6 columns. This is not a coincidence. The orange here are the D block. There are 10 columns. The D subshell can hold 10 electrons. And down here, these are the F block elements. There's 14 for the 14 electrons that fit in the 7 orbitals of that subshell. Okay, so how do you use this? Well, you pretend that you're just counting across. The periods here correspond to the floors in the hotel or the principal shells. So 1, 2, 3, 4, etc. So hydrogen has 1 electron. It's in the 1s orbital. So 1s1. There's its little electron configuration. Helium, here we're 1. This is the S block, 1, 2. So 1s2. Then we would come down here for lithium. It would be 1s2, 2s1. And then beryllium adds another electron, 2s2. After that, you move over here to the P block. This is the 2p room over here. How many people are staying in it? Well, if we were looking at oxygen, it'd be 1, 2, 3, 4 people. So 2p4. Do you see it at all?
No.
No. Honest answer.
How come in the P block is S?
You mean, why does it say 2s2 here? Okay, that's because what they're showing here is the valence electrons. Where are the valence electrons? So we learned that boron, being in group 3A, has 3 valence electrons. Well, 2 of them are over here, and 1 of them is here. So the 2s fills up, and then the 2p has 1 electron in it. So I'm gonna go ahead and do some examples, and hopefully it'll become clearer, and we can come back to this. This is just a summary. Lower energy orbitals fill before higher energy. The cheaper rooms in the hotel fill before the more expensive ones. Orbitals can hold no more than 2 electrons each. The beds in the hotel can hold no more than 2 people. When 2 electrons occupy the same orbital, they must have opposing spins. When 2 people sleep in the same bed, they have to sleep head to toe. When orbitals of identical energy are available, all of these are first occupied singly by electrons with parallel spins rather than electrons in pairs. So in the room, imagine we're going into the 3p room. There's 3 beds. 2 people are going in. Are they going to choose to sleep head to toe in one bed when there's 2 empty beds over there? No, they wouldn't do that. They're both going to take their own bed, and the first person in the bed is going to choose to sleep right side up, right? Because that's what we're more comfortable with, unless you're one of my kids. But we prefer to sleep with our head by the headboard, right? And so that's what the electrons do. They'll take their own orbital if they can. But then they'll pair up rather than spending more money to go to a next higher orbital. So let's look at nitrogen, oxygen, fluorine, and neon. Where'd that go? Okay, so here's nitrogen on the periodic table. Okay, so nitrogen has 7 electrons. Where are they? Well, there are 7 blocks here. 1, 2, 3, 4, 5, 6, 7. So here, this is period 1. This is the S block, and helium kind of belongs over here. So 1s, 2. And then the next row is the second row, 2s2. And then nitrogen comes over here. And this is P, 2p, 1, 2, 3. 2p3. So let's draw that. Again, I prefer to do the orbital diagrams first. So nitrogen has 7 electrons. So on the first floor of the hotel, there's 1 room with 1 bed. On the second floor, there are 2 rooms. The S room has 1 bed. The P room has 3 beds. And so these boxes that represent the orbitals are like the beds in the hotel. Yes?
And when you say 7 blocks, so for an element, would you figure out its period or its atomic number and say it has that many
Well,
blocks?
no, I'm just looking at, this is element number 7. It has 7 electrons. And we can use these squares on the periodic table. I probably shouldn't have called them blocks. We can use the squares on the periodic table to represent where those 7 electrons are. So I think of this as counting along. 1, 2, those are both in the 1s orbital. And this is the 2s orbital. There's 1, 2 there, so I've got a total of 4. And then 1, 2, 3, I've got 3 of them over here in the 2p subshell.
Will that always work?
It'll always work. Mm-hmm. So the 1s, 2s, and 2p, at this point we're not worrying too much about order because it's making sense still. It hasn't gotten jumbled up. And next would be 3s. The first level has 1 sublevel, subshell, the S. The second shell, 2, has 2 subshells, S and P. The third one has 3, S, P, and D. But after we can go, after 3P, the order gets jumbled. But until then, we're okay. There's a D, and then the 4 would have S, P, D, and F, but the order gets mixed up. So, are you okay with the boxes here?
It always goes in that order, like 1s to
Always the same order.
You go from 1s to 2p because it's on the second floor, and then it goes up to 3 because it's on the third floor.
No.
Well, it's 1s, and then on the second floor, there's 2s and 2p, and then you go up to the third floor, 3s and 3p, and then after that, things get a little jumbled up. And we need to get the main idea first, and then we'll see about the jumbling. So,
I have a question.
yeah.
And so, since nitrogen is only on the second row of the periodic table, it would seem that there's no principal shell 3 where electrons are. So do you just look at the number of electrons left to figure out if it goes up another floor?
Well, so we're always going to write the ground state. So that's all of the electrons in the lowest possible energy levels. And so yes, because nitrogen is in period 2, it's not going to have any electrons in the third shell. Now, does that mean that those orbitals don't exist? No, they do. Just like in a hotel, if people aren't staying on the third floor, those rooms don't disappear. They're just empty, right? Do we need to write them down all the time? Absolutely not. But are they there? Yeah. And so what I've drawn here is more boxes than I need for nitrogen, but just to show you what's going on here, that there's the S, and on the second floor S and P, and on the third floor S and P, and then there's a D, but we're not going to worry about the rest of it yet.
So does the row always determine the number of
The row always determines the highest shell that has any electrons in it. Yep. And those are considered the valence electrons. So for nitrogen, what we do here, we've got 7 electrons. We're going to imagine the electron people coming in to stay in the hotel. Each box is a bed. Okay? I'll make them red, because that's what your book does. So the first electron is going to take the bed in the first room. The second electron comes in. He's not crazy about sharing the bed, but electrons are cheap. Okay? They're going to share rather than spend more money. So he's like, well, I'll take that spot. Sleep upside down. Third electron comes in. He's like, cool, I get my own bed. Fourth electron comes in. No, you don't. I'm going to share with you. Okay, so fifth electron. Now we're up into the P room that has 3 different beds in it. So I've got 1, 2, 3, 4, 5 electrons. Number 6 comes in. He's going to take his own bed, right? Because that's what people would do. Why sleep with a stranger if you don't have to, right? Okay, so there's 6. Number 7 comes in. Is he going to share with one of these guys? No, he's going to take his own. Okay? So 7. There's our 7 electrons. So that's the orbital diagram. Okay? The electron configuration is like what the front desk clerk has written down, just real fast shorthand, so he knows where all the people are, so he doesn't send someone to a room that's already full. So 1s has 2 electrons. So for nitrogen, we've got 1s2. The 2s room has 2 in it. 2s2. This is the 2p room, and there are 3 electrons. So 2p3. If you take these superscripts and add them up, 2 plus 2 plus 3 equals 7. Everyone's accounted for. So let's look at the periodic table again. So here's nitrogen. All right, there's nitrogen. Nitrogen is in the P block. This is the P block over here. And it's on the second row, the second period. So that tells me that its electron configuration ends with 2p something. And I can tell what the superscript is by counting. 1, 2, 3. This ends with 2p3. This ends with 2p4, 2p5, and 2p6. And everything before the p is full. The 1s is full with 2, the 2s is full with 2, or you can think of counting across. 1s, 2, 2s, there's 2. This is 2p, 1, 2, 3, 2p3. Anybody seeing it?
Yeah.
Okay, is it getting better? So oxygen would be 1s2, 2s2, 2p, 1, 2, 3, 4. And fluorine would end in 2p5, neon would end in 2p6. Okay? I think I lost my writing. Yeah, it's gone. Well, we did nitrogen.
Why does it have the 1s2 on the periodic table? When you read it?
That's a good question. So, like here, why doesn't it show 1s2? So what they're showing under the element here is just the electron configuration of the highest row. So it's not showing, here it's just showing things that are in the second row. Here it's just showing things that are happening in this 5th row. Because there wouldn't be room for everything on the table. Good question.
So we have to memorize what the 1s, the 2s, and how many rows in each.
Well, you don't have to memorize because it's all hiding in the periodic table here. So S is always 2 electrons because there's 2 columns here. 1, 2. So there's always 2 electrons that can fit into an s orbital, or an s subshell. Over here, p, there's 6 columns. In the p subshell, you can put 6 electrons. There's 6 columns. Yes?
Don't the A groups also coincide with how many covalent electrons there are?
It also corresponds to valence electrons, yeah. And we're going to talk about those in a minute. D is 10, and you can just count across. There's 10 columns there. And this is F, and there's 14 columns. So it's all right there. So let's do fluorine. So fluorine has how many electrons? 9 electrons. So if we're going to do the orbital diagram, there's going to be the 1s and the 2s and the 2p. And we can tell by looking at the periodic table, fluorine being close to the end of the second period, that we don't have to draw boxes for 3 or 4 or anything higher than 2. Because that is the end of the second floor of the hotel. So putting 9 electrons in here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. They take their own bed first, sleeping right side up, and then they pair up. The electrons take orbitals to themselves with upspin before they pair up and have opposite spins. And so then if we write the electron configuration for this, it's 1s2, 2s2, 2p, how many? 5. There's 5 electrons in the 2p subshell, 2 in the 2s, and 2 in the 1s. Any questions? So what about neon? Neon has 1 more electron, right? So let's make this neon instead. Neon has 10 electrons. Well, is it really that much different? No, we just stick 1 more electron in there. And then instead of a 5 here, it's a 6. That's it. Once you see it, it's almost ridiculously simple. So how I picture it is, as we're going across, looking at the different elements, I imagine, okay, I'm just adding an electron. I'm just adding 1 more electron, 1 more electron. And they always follow the same path, the pattern of where they're going in. And the periodic table actually tells us where they're going. So what we see here is that the electron configuration for neon represents completely filling the n equals 2 principal shell. So 2s2, 2p6, those are the 2 rooms on the second floor. They're both full. The first floor is full, the second floor is full. It turns out that that is a particularly stable set of circumstances. In terms of, more scientific talking, it's an especially low energy state. In terms of the hotel, there's like some sort of a bonus going on that if you fill up the floor, you save money or something. Some Groupon deal, I think. So you can imagine that if you went on and on and on, those electron configurations could get pretty long, right? So we have a shorthand notation. So we use the noble gases, and then we just write what's after them. So for sodium, let's go back to the periodic table. So here's sodium. Sodium has 11 electrons. It has 1 more electron than neon. So what we can do, instead of writing all of that 1s2, 2s2, 2p6, we can just write neon in brackets. That stands for the electron configuration of neon, and then we write what comes after it. So here's sodium. It's got one more electron. In terms of our block understanding of this, this is in the S block, right, on the third level, period 3. So this is 3s. It's the first one, so it would be 3s1. So we just write neon in parentheses, in brackets, and write what comes after it.
Magnesium being neon in brackets.
Yep. Magnesium would be neon in brackets, 3s2. I should write it on the other slide, but I'm writing it on this slide. So for sodium, we would write neon in brackets. That stands for the electron configuration of neon, 3s1. And if we wanted to do, bless you, magnesium would be neon plus 2 electrons, so 3s2. What would rubidium be?
Are we always using neon?
No. You're using the previous noble gas, the closest one. So both of these are just a little bit past neon. So what if we did rubidium? It'd be krypton. Okay, so for the noble gas shorthand, you're looking at what's the previous noble gas. So one way to do that is just move up a row and go all the way to the end, krypton. So rubidium would be the electron configuration of krypton plus, this is period 5 in the S block, and it's the first square, 5s1. So what would strontium be?
5s2.
Yeah, krypton 5s2. Okay, yeah.
Now, if you didn't use the noble gas configuration, you would have that mix up between like 4s back to
Yeah.
2p, then
We'll get to that. Does somebody else have a question? So the shorthand does save us a lot of writing for the larger ones. And it's just whichever noble gas is the closest, and then you write whatever's coming after that.
So how do you know which ones are long and when to use that and when to use the other one?
The question would tell you. So on the exam, it's multiple choice. And so I'm not going to try to trick you. It will either be all different choices with the shorthand, or it'll be all different choices with the long, completely written out. On worksheets, it'll tell you.
So you know how you put like 5s2.
Mm-hmm.
So if we had like more and not only 2, why is it only like, why is it only 2?
Well, because strontium is only 2 electrons past krypton. So let's look at maybe silicon. Okay, so what's the noble gas immediately before silicon? Neon. So this is going to be neon. I'll write it down here. Silicon. It's going to be neon plus, so after neon, this is 3s, and there's 2 electrons in there. So 3s2. And then this is the 3p block. There's 2 electrons over here. 3p2.
So we're always going to use like the noble gases and the S, like
For the shorthand, you're going to use the noble gas, and then you come to the next row, and you just follow along. You go as far as you need to until you get to the element you're doing. Mm-hmm.
For like, when you get to like the 4th period and whatnot, do you have to write out like 4s, 3d, 4p?
Yeah, we'll get to that in a minute.
Okay.
I'm ignoring that for now. Because I want you to get this part straight in your head before we get into the Ds. Any questions? Okay.
How about chlorine? Would it use neon also?
Chlorine would also use neon. Yeah. You can't say argon minus something. So it would be neon plus the extras. So it would be neon plus 3s2 and 3p5. So what this ends up being, what's shown on this periodic table, is this is what you would write after the noble gas. Well, for most of them. Scratch that. It's a mess. Never mind. Okay, we did that. Okay, so write electron configurations for each element. Now, it doesn't say noble gas shorthand, but it doesn't say full electron configurations either. Let's do the full ones, though. So for aluminum, find it on the periodic table. What block is it in? S, P, D, or F? It's in the P block, okay? That tells me that its electron configuration is going to end with P something. What period of the periodic table is it in? The third period, right? So it's going to end in 3p. So starting with hydrogen and helium, that would be 1s2. And then you go to lithium and beryllium, that's 2s2. And then we go boron through neon, would be 2p6. And we come down to the third row, 3s2 for sodium and magnesium. And the next one over is aluminum, so that's 3p. And we're just in the first of that block, and so it's 3p1. If you add these exponents up, these superscripts up, they should add up to 13, which is the number of electrons that aluminum has. Now, if we wanted to use the noble gas shorthand, it would be neon, right? Neon, and then the stuff that comes after neon, 3s2, 3p1. Because what we're doing there is we're saying, well, this part, that is the electron configuration of neon, isn't it? 1s2, 2s2, 2p6. Instead of writing all of that, I'm just going to write neon in brackets. Any questions? Did not mean to do that. Wrong button. I wanted to just do that. Okay. Bromine. Dang. I want to do bromine yet. I rearranged the slides and I see that I didn't do a good job of rearranging the slides. Let's come back to this in a minute. Okay, so now I got to tell you about those d orbitals. So for S and for P, the period number gives us the number that goes in front of whatever we're looking at here. So these are 3s, they're in the third row. These are 3p, they're in the third period, the third row, 4, 5, 6, etc. The D level, now this is how I think of it. I think of it as, it looks like the D level kind of sank. Like it should be up here, right? And then you're coming down the stairs, here's one, and you go down, and you go down, and it's more symmetrical that way, right? But it's like the floor of the valley that now the water table has dropped so far, the land is sinking, right? So here is the Central Valley of California, and it has sunk. So this isn't the 4D block, this is the 3D block. So for the D block elements, so this represents n equals 1, n equals 2, etc. For the D block, it's n minus 1. So this is the fourth period. In here, this isn't 4D, this is 4 minus 1. So this is 3D. This isn't 5D, it's 5 minus 1. 4D, 5D, and 6D. Okay with that? Of course, it doesn't really matter if you're okay with it or not because it's just how it is. And then the F, I'll tell you about the Fs, we're not really going to go there. The Fs fit in this little gap here. We should take a pair of scissors, cut this, and spread it open. And so the F block is also sunken. And it's 1 lower than the D, and so for the F block, it's N minus 2. So cerium here, number 58, is actually in period 6 of the periodic table. 6 minus 2 is 4. This is filling up the 4F block. Okay. So the order is all here. If you can remember, this is minus 1 and this is minus 2. So 3S, 3P, 4S, 3D, 4P, 5S, 4D, 5P, 6S, 4F, 5D, 6P, 7S, 6D, 5F, 6D. Right? Crazy. Okay, so let's go back and do bromine. So bromine, find bromine on the periodic table. It's in period 4, right? Over in the P block. And you can count in that P block, it's 1, 2, 3, 4, 5. So just by its position on the periodic table, I can predict that, not 5, it's going to end with 4p5. Because if you've got like coordinates set up on the periodic table, it's in 4p5. So if we are going to do, let's do the noble gas shorthand first this time. What's the noble gas right before bromine? Argon. So argon, and then we look what's coming after argon. So we're going, argon's the end of the third row. So we go to the fourth row, and we've got the 4s. So we've got the 4s, and that's going to get full with 2 electrons. Then we get into those d electrons. But they sank down. They're not the 4th level, they're the 3rd level. So this is 3d, and we have to go all the way across. So it's going to be full, 10. And then we get into the 4p, and 1, 2, 3, 4, 5. So that's the noble gas shorthand electron configuration for bromine. If we write the whole thing out, 1s2, 2s2, 2p6, 3s2, 3p6. Then it goes to 4s2, 3d10, 4p5.
How come the 4p5 goes before the 8r?
Oh, this, it doesn't. This was my prediction.
Where did that 10 come from?
The 10 came from going all the way across from scandium to zinc on the 4th row.
From which one is that?
From here to here. So we're going to bromine over here. So we started at argon, and then here we've got 4s, there's 2 here, and then we've got the 3d. So 3d, and you count across, there's 10 of them. I'll spare you listening to me count to 10. And then this is 4 again, 4p, 1, 2, 3, 4, 5. So it is confusing that the 3D subshell is lower in energy, higher in energy than the 4s. But that's just how it is. It's because of the interaction between the electrons causes that to be lower in energy. In the hotel analogy, there's something less desirable about the 4S room. Maybe it's closer to the elevator and so it's louder. And so they're going to give you the 4S room a little cheaper than the 3D room because the 3D room's quieter. I don't know, make something up. Let's do strontium. What's the noble gas before strontium? Krypton. So there's krypton, and then after krypton, we're getting into the 5th level, right? So 5, the first blocks we come to there are the S, and strontium is in the second one, so 5s2, and that's it. But what if we do the whole thing? Do we have to? We gotta practice. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Yeah, this one seems out of place, right? So if you like that line drawing thing, this thing, you can do that. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. This will give you the same order. What I'm doing mentally is seeing the periodic table, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. This is D, but it's sank. 3d, 10. Now these aren't sunken. 4p6. Here's 5, 5s2. Next up would be 4d. Going all the way across would be 4d10. Then we're back to 5p. 5p6, and here this would be 6s2. Barium is the farthest I would ask you to go on an exam. I would not ask you to go past barium. Because in Chem 3A, we can leave the F's out. Pardon me? Yes, you might have to write the whole thing out for barium. Now the worksheet, I don't remember what's on the worksheet. The worksheets are crazy. Just do the best you can. Any questions? Orbital diagram. Let's do an orbital diagram for argon. So argon is at the end of the 3rd period. So we only need boxes up to 3p, right? We need 1s for the first row, 2s and 2p for the second row, 3s and 3p for the third row. Argon has 18 electrons. So then we go fill them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Orbital diagram for argon.
So for the P, it's only 3 boxes, right?
For the P, it's 3 boxes. Because there are 3 orbitals in the P subshell. There are 3 beds in the 3P room. But you can put 6 people in there, 6 electrons.
So do you usually put one down and then count backwards, or how do you know that each one is going to need 2 people in the bed?
Because it's only, people only sleep 2 in a bed. I mean, having 3 or 4 people sleep in a bed is very weird, in this country at least. I tried to get 3 of my kids to sleep in a big bed in the hotel. They wouldn't do it. There was room for them. They could have slept sideways, but they wouldn't do it. 2. 2's the most. There can only be 2 electrons in an orbital because there are reasons, but we don't want to go there. We don't. Okay.